Yeah, hello everyone. Good morning for those of you on the East Coast. Yeah, thank you very much for the introduction and thank you for the invitation to speak. I'm very excited to be able to share an overview of our MIP star equals RE results, which is joint work with Zhangfeng Ji, Anand Natarajan, Toma Vidic, and John Wright. So I'm not going to assume any particular background in computer science or quantum information theory, but if anything is unclear, please feel free to ask in the chat or even just pipe up and ask. Okay, so this talk is about the connection between three questions that seem at first glance very different from each other. One is a well-known question from operator algebras known as the Connes Embedding Problem, and it asks if every separable finite von Neumann factor can be embedded into an ultra power of the hyperfinite type 2-1 factor. Another problem is Sirelson's problem coming from quantum information theory, and it asks if all quantum commuting correlations can be approximated in finite dimensions. And finally, the third is a question about complexity theory. And it asks if there's an algorithm to approximate the value of something called a non-local game. And over the past 10 years or so, we've learned that surprisingly, these three questions are intimately linked. So through a sequence of papers, starting from Kirchberg in the 90s, then about 10 years ago, due to Fritz, Yuen et al. And Ozawa, we know that there's a positive answer to the Connes embedding problem, if and only if there's a positive answer to Sirelson's problem. And furthermore, if these two questions have a positive answer, this in turn implies existence of an algorithm for non-local games. So in this talk, I won't discuss von Neumann algebras and the Connes embedding conjecture at all. But instead, I'll focus on the connection between Sirelson's problem and this complexity question about non-local games. And ultimately, our results, MIP star equals RE, rules out the existence of an algorithm for non-local games, which implies that Sirelson's problem and therefore Connes embedding problem has a negative answer. So to explain this connection, let me start off by explaining quantum correlations and Sirelson's problem. So what is a correlation? So it's a mathematical model for the behavior of a physics experiment involving two separated systems. I'll call them box A and box B. And each box takes in an input, one of n symbols, and each box produces an output, one of k symbols. So in physics terms, we should think of each input as telling the box to perform a specific measurement on whatever is inside the box. And the output is going to be the outcome of the measurement. And we can describe the joint input and output behavior of these two boxes together using a conditional probability distribution, P of AB given XY. So A and B are the outputs, X and Y are the inputs to the two boxes. And we could represent correlations as vectors in real space. So these are going to be four tuples of inputs and outputs. And in this talk, we want to think of these boxes as being separated very far from each other. So they can't send signals to each other. But despite being separated, the boxes can behave non-independently. And the question is, what kind of correlations are allowed by physics? So we believe that nature is described by quantum physics, and the theory of quantum mechanics has a mathematical prescription of what correlations can be realized between these two separated boxes. So we'll call a correlation P quantum if it can be expressed as this inner product formula here. And what do these symbols mean? Well, this psi is going to be a unit vector in the tensor product of two Hilbert spaces, HA and HB. These are finite dimensional Hilbert spaces. And HA is going to represent the physical state space of box A. HB is going to represent the physical state space of box B. And when you take the tensor product of these state spaces, you then can talk about the state of the boxes jointly. And these, the AXA and BYB are positive operators acting on the respective Hilbert spaces. And they have the property that if you fix an input, such as X, and you sum over all the outputs A, then the sum of the operators AXA is equal to the identity. And a similar normalization conditions hold for the operators B. And we think of these operators as representing measurements that the boxes can perform. And this normalization condition just enforces the fact that what you get is a valid conditional probability distribution. The tensor product structure here models the spatial separation between the boxes. So this is one way of modeling correlations in quantum mechanics. And we can collect all of these correlations, these P, A, B, X, Y's together into a set called C sub Q. It's a function of the number of inputs and outputs, and we'll call this the quantum correlation set. It's all the finite dimensional quantum correlations. I'll introduce another set called C sub QA, CQA. And this is going to be the closure of C sub Q. And we should think of CQA as representing all the correlations that can be approximated by finite dimensional quantum correlations. So it turns out that that wasn't the only way to model correlations allowable by quantum physics. There's a more general way, and this is called the commuting operator model. I call a correlation quantum commuting if it's equal to a similar looking inner product formula. But here, instead of having two separate state spaces, two Hilbert spaces, you just have one single Hilbert space H. It's possibly infinite dimensional. And the operators AXA and BYB act on the same Hilbert space. We just have the condition that the operators AXA and BYB commute for all possible combinations of X, Y, A, and B. This model captures the tensor product model, the finite dimensional model that I described before, but it may include more types of correlations. This commuting operator model is motivated by the study of quantum field theories. It's where, in quantum field theories, if you're given two, physical systems where, they're causally independent, it's still not a priori clear how to decompose their state space into a tensor product of two Hilbert spaces. But this commutation conditions captures the notion that the order of measurements don't matter. So we can combine all of these correlations together into a set called CQC. It's a set of all quantum commuting correlations. Okay, so I've described a bunch of correlation sets, and they form this chain of inclusions. So on the very left, we have the set CQ, which is all the finite dimensional correlations. You take its closure, you get the approximately finite dimensional quantum correlations. And all of that is contained in the commuting operator correlations. And so a natural question is, are any of these inclusions strict? So about 3 years ago, William Slostra showed that the first two sets are different. So CQ is not closed. It's different from CQA. And this was a breakthrough work. And the question of whether the second inclusion holds is known as Cyrilson's problem. So is CQA equal to CQC? And what this question is asking is, can every infinite dimensional commuting operator correlation be approximated in finite dimensions? And it's important to note that if you take commuting operator correlations but restrict them to be finite dimensional, so there's no tensor product condition, but you have this finite dimensional condition, it's the same as CQ. Okay, So in order for there to be a hope of CQC being different from CQA, then you would necessarily need an infinite dimensional correlation to separate the two. Okay, so this is Syrelson's problem, and it was formulated, I think, sometime in the early 2000s. And as I mentioned about 10 years ago, Fritz and Yuen et al. Independently showed that a positive answer to something known as Kirchberg's QWEP problem, which is a question about C-star algebras, implies a positive answer to Syrelson's problem. So what is this QWEP conjecture? It asks, it asks if the minimal and maximal tensor products of the group C-star algebra on the free group on countably infinitely many generators, whether these two tensor products are equivalent. And if they are, then Syrelson's problem has a positive answer. CQA is indeed equal to CQC. And a few years later, Ozawa proved the converse. So in fact, Kirchberg's QWEP problem and Syrelson's problem are equivalent questions. And as many of you know, this QWEP conjecture was proved by Kirchberg in the 90s to be equivalent to the Connes embedding conjecture. Okay. So this links this question in quantum information theory back to the Connes embedding problem. All right, so that's quantum correlations and Syrelson's problem. Now let me turn to non-local games. So non-local games are an operational way of thinking about things that you can do with these quantum correlations. Okay, so let me talk about two-player non-local games. And formally, these are, it's a pair of two things. It's a question distribution over some question alphabet Q. In this game, what happens is at the beginning, you have these two boxes A and B. They possibly share some quantum correlation, and a pair of inputs X and Y are sampled from this distribution mu. Okay, they're given to the boxes. X is given to A, Y is given to B. And these boxes are supposed to produce two answers, A and B, which are returned to this decision predicate D that determines whether the boxes win or not. So the decision predicate's a function of the questions and answers in this game. The players win if D of X, Y, A, B is equal to 1. And the players are allowed to share some correlation to play this game. So we think of the correlation that they share as some kind of strategy that they employ during the course of this game. So if you walk up to me with a game G, and you say that the players share some correlation P of AB given XY, then you can measure their success probability in this game using the following formula. So this omega of G comma P is the probability that if you sample questions X and Y according to this distribution mu, and they produce answers A and B according to their correlation, that they generate a winning pair of answers. Okay. And let's see. So was there a question in the chat? So, how well they can win depends on what types of correlations you allow them to use. So if you allow the players to use correlations from the set CQ, we can define something called the quantum value. I'll call it omega sub Q. And this is where you take the supremum over all correlations in the set C sub Q. And this is going to be the same as taking the supremum over the set CQA. Okay, so this is called the quantum value. And it's, you should think of it as being the maximum success probability that they can achieve if they're allowed to use finite dimensional quantum strategies or finite quantum correlations. We can also talk about something called the commuting operator value, omega QC. This is where you take the supremum over this this more general set Q is at most omega QC for all games G. And if Searlson's problem has a positive answer, then these two values are going to be equal always. Right. So let me give a concrete example of a non-local game. Perhaps the most famous non-local game is known as the CHSH game. And this was formulated by some physicists in the late 60s, Clauser, Horn, Shimony, and Holt. And they formulated it as an experimental test of whether nature is describable by classical physics. So the game is quite simple. The question distribution is over 2 bits x and y that are uniformly random and they're independent. The answers are also going to be bits. And the decision predicate says that the players win if and only if the sum of their answer bits is equal to the product of their question bits modulo 2. And what are the properties of this game? Well, if the players, these boxes, behave according to classical physics, then the maximum success probability that they can have is 3/4. So this gives rise to something I'll call the classical value of the CHSH game. And this is where they're restricted to using classical correlations. So I didn't define what classical correlations are, but you can think of them as being quantum correlations where all the POVM operators that they use are diagonal matrices. On the other hand, quantum theory predicts that it's possible to have a higher winning probability. So the omega Q and the omega QC value of the CHSH game is strictly greater than 3/4. It's roughly 0.854. And kind of the amazing thing is that this has been experimentally tested. So people actually set up physical experiments to play the CHSH game, and they do observe a winning probability that's greater than 3/4, which tells you that nature doesn't behave according to classical physics. All right, so before I go on, are there any questions about quantum correlations or non-local games? All right, so this takes me to the next part of the talk in which I talk about the computability aspects of non-local games. So also in the early 2000s, some computer scientists, Richard Cleve, Hoyer, Toner, and Watrous, who were studying this interplay between computational complexity theory and quantum information, asked the following question about non-local games. They asked, is there an algorithm to approximate this omega Q value? So what they had in mind is it possible to write a computer program that takes an input, some description of a non-local game G, maybe a precision parameter epsilon, and the computer program will output an additive estimate of omega Q of G. So it's a pretty natural question from say, a computer science point of view. And if you had an answer to this, then there's a bunch of natural follow-up questions. Like if there is an algorithm, then what's the fastest algorithm? Or if you could approximate this omega Q value, what other problems could you solve? Could you reduce this approximation problem to, say, some other problem? And maybe just to provide a little extra motivation for why this question is a very natural one, let me explain how this is motivated by some classical or non-quantum theoretical computer science. So in the 1970s, Steve Cook famously came up with the notion of NP completeness. And one way of formulating what he proved is he showed that computing the classical value, the maximum success probability of non-local games using classical correlations, to compute this value exactly is an NP complete problem. He didn't phrase it this way, but this is one way of formulating what he proved. And about 20 years later, people asked, well, what about approximating this maximum success probability, at least classically, this omega c? And people showed that approximating it is still an NP-complete problem. Okay. And this result is known as this hardness of approximation is known as the probabilistically checkable proofs theorem, or the PCP theorem. And a more common formulation of the PCP theorem, maybe you've come across this before, is it says that proofs of mathematical statements can be encoded in a robust format such that the correctness of this proof can be checked by examining only 3 bits of the proof at random. So this is kind of an amazing statement, and it's something that I'll get back to later in the talk. So coming back to this question of an algorithm for approximating omega q. So there's some barriers that one immediately faces when thinking about this problem. So in the case of approximating this or computing this classical value omega c, there's going to be a trivial algorithm to compute this value in exponential time. Okay. So one can simply enumerate over all possible deterministic strategies for players in a given game. And if someone walks up to you with a game, you know how many questions and answers are involved in the game. So there's going to be a finite number of deterministic strategies for the game. So it's possible to enumerate over all of them in finite time. But for the quantum value of games, it's not clear if there's a similar brute force algorithm. And actually, in 2017, as a consequence of showing that the set of quantum correlations was not closed, William Slofter showed that there's no algorithm whatsoever to compute this omega q value exactly. Okay. So this gives some evidence that this set of quantum correlations is, it's very different in terms of complexity than the set of classical correlations, for example. So, omega q is impossible to compute exactly, but what about approximating it? And, the trouble there is, there's no generic upper bound on the dimension of strategy that you would need to consider to win, optimally or nearly optimally in any given non-local game G. So, if you were to try to do this trivial, enumeration over all possible strategies, you wouldn't know what dimension to consider, right? You know that there's some finite dimensional strategy that comes with an epsilon of omega q, but you wouldn't know what dimension that was. So going back to, this Connes embedding and Symposium's problem, which I mentioned, these are the equivalent. If they had a positive answer, it would actually imply that there is an algorithm to approximate omega q. So let me quickly go over how this algorithm works. So it combines these 2 procedures, which I'll call search from below and search from above. And the search from below procedure is pretty easy to explain. It's this attempt at trying to do this brute force enumeration over all finite dimensional strategies. So see a question in the chat. How is it possible that calculating omega q is NP complete, but there's no algorithm for it? It's known that calculating omega, not omega q, but the classical value omega c. So this is where you restrict yourself to considering classical correlations, which essentially you can think of it again as quantum strategies where all the strategy POVM elements are diagonal. So that one turns out to be an NP complete problem, because it reduces to the case of just considering deterministic strategies. Okay, so the search from below procedure is going to compute an infinite sequence of non-decreasing numbers, alpha 1, alpha 2, alpha 3. These are all going to be lower bounds on omega q. And alpha d is going to be the an epsilon approximation to the best d-dimensional strategy for a given non-local game G. And if you fix D, then you can actually compute alpha D. You can, for example, search over an epsilon net on the space of d-dimensional correlations, which you can do in finite time. And it's easy to see that as you increase D, eventually you're going to approach this omega Q value. Right, so the search from below procedure will just enumerate over these alpha Ds. The search from above procedure will compute a non-increasing sequence of upper bounds on the commuting operator value of a game, the omega QC value of G. And these beta values, if you fix D, this is going to be the best upper bound on the commuting operator value of the game that is certifiable by sums of squares of degree D polynomials and non-commutative variables. The important thing about this beta D quantity is that it's also computable by a technique called semi-definite programming. And one of the things we know about these beta Ds is that they also converge to the commuting operator value of a game as you increase the degree to infinity. So putting these two procedures together, we get an algorithm to approximate a omega Q, assuming a positive answer to Searlson's problem. So you'll just compute these two sequences of numbers, alpha D and beta D. And if at some point they come within epsilon of each other, you know that you've converged on the quantum value of the game. And if CQA is equal to CQC, then you know in fact that this algorithm will indeed converge at some point. There's no guarantees of the convergence rate, but you know at some finite time it will converge. Okay. So this is how positive answer to Searlson's problem implies an algorithm. Okay, so this brings me to the main statement of our results, MIP star equals RE. And what it says is, it says there exists some computable map between Turing machines M, or you think of Turing machines as computer programs, to non-local games G sub M, with the property that if the Turing machine M halts in some finite time, then the quantum value, omega Q of G sub M is equal to 1. But if M does not halt, meaning that if you just run the program and it just runs forever, then the quantum value of G sub M is at most 1/2. This quantity 1/2 is not so important. It can be replaced by any constant that's less than 1. Okay, so what are the implications of this statement? Well, we know from way back in 1936 that there is no algorithm to solve the halting problem. There's no algorithm that can determine if any given Turing machine halts or not. So in particular, it means that there's no algorithm to approximate the omega Q value of any game for any epsilon. So in particular, this search from above and search below algorithm cannot converge for all G. I mean, if you could approximate omega Q, then you could actually, using this reduction I just described, distinguish between whether a Turing machine halts or not. So if this search above, search below algorithm doesn't converge for all games, then there must be some game where the quantum value and the commuting operator value differ, which implies a negative answer to Searlson's problem. And therefore, the Connes embedding conjecture is false, or the problem has a negative answer. So are there any questions about this chain of implications here? Okay, so let's see. So a question is, given a game G, do you have any conditions for when the algorithm to approximate omega Q will converge? I guess essentially the convergence is equivalent to the omega Q and omega QC values being close together or equal. If they're not equal, then you know, the upper bound and the lower bounds will just sort of get stuck and never come close to each other. All right, so let me you know, explore the implications just in a little more detail. So you know, as I mentioned, this chain of reasoning implies that there's some game out there that have a differing quantum and commuting operator value. So you know, what this means is that for this game, whatever it is, there's some infinite dimensional commuting operator strategy for this game that has some success probability that cannot be approximated by any finite dimensional strategy. So, you know, from a physics point of view, this is very interesting because it shows that, at least in principle, there's an experimental test for infinite dimensional physical systems. If you had this game G, you could imagine playing it with these two boxes that are separated from each other. And if you saw that these boxes were consistently winning this game G with probability that's close to omega QC, then this would tell you, give you a lot of evidence that these boxes cannot be modeled by any finite dimensional physical description, which would be really interesting. No, but our result doesn't actually say how to carry out this experiment in the real world. And in fact, I think a lot of physicists believe that you know, essentially any physical experiment that you could run just by what we know from, you know, quantum field theory, you know, can be described approximately by, you know, finite dimensional descriptions. But still, this is an intriguing possibility nonetheless. An interesting question is whether, you know, what is this game G that has these differing values? Can one come up with an explicit counterexample? So this is related to this question of, you know, we have this reduction from Turing machines M to non-local games G sub M. So you can ask, well, for which Turing machines M are those for which the quantum and commuting operator values differ? And what should be the case, and we don't know that this is true, it should be that if you take a Turing machine that does not halt, then this should give you a separating game. So we know, you know, from the reduction I described, the quantum value of a non-halting, you know, for GM for a non-halting M is at least a half, but it should be that the commuting operator value of this game is 1. So in particular, you could take the Turing machine that just gets, you know, stuck in an infinite loop just from the get-go. We don't know how to show this, but using a similar construction, we can come up with a game G that does have this property. Okay. You know, what are some properties of this game? So this explicit separating example G, it's an example of something called a synchronous non-local game, if you know what that is. And by an early result of Paulson, Severini, Stalky, Todorov, and Winter, if, you know, for the specific game that we wrote down, if you can describe this commuting operator strategy in some explicit way that achieves winning probability 1, then this would directly yield an algebra without the Connes embedding property. So we don't know how to write this. You know, we know that it has a value 1 commuting operator strategy, but we don't know how to describe it algebraically or you know, give some nice description of it. Part of the challenge is that this game G is pretty complicated. You know, we tried to do some rough accounting of the number of questions and answers in this game, and it's probably less than 10 to the 20, but you know, we're not really sure. And part of the reason it's so complicated is that this description of this game involves some Turing machine that executes this semi-definite programming hierarchy. And you know, I've never programmed this before, but I imagine it probably involves a fair amount of Turing machine code. So this game is probably pretty complicated. All right. Okay. So So this last part of the talk, I'm going to try to give some glimpse into how this reduction works. How do we transform Turing machines to non-local games in a way that captures whether the Turing machine halts or not. And this relies on a technique that we call recursive compression of non-local games. So in order to describe this compression technique, I'll have to explain how we represent non-local games using Turing machines. I mean, after all, we want to convert Turing machines to non-local games, so it kind of makes sense that we want to describe non-local games in terms of Turing machines. So, recall that a non-local game has, two pieces of information. It has this question distribution x and y, mu of x and y. Also has this decision predicate d of x, y, a, b. And I want to imagine that these non-local games are represented by Turing machines that specify the, how do you sample from this question distribution mu, and how do you compute this decision predicate d? Okay, so just imagine that we have some computer program that will compute how, the sampling procedure and also this decision predicate. So if we represent non-local games in this way, then this gives rise to a complexity measure for games. And this is going to be an upper bound on the running time of this verifier, this computer program that computes all of this information. Okay. And just to introduce a little bit more notation, I want to talk about an infinite family of non-local games G1, G2, G3 as being uniformly generated if there exists a single Turing machine, G hat, that will tell you the description of each of the individual games, Gn. So this Turing machine G hat, you stick in an index n, it will tell you about the nth game in this family. Okay, so there's a single object, this G hat, that tells you about an infinite number of games. Okay, the next piece of notation is something that I'll call the entanglement lower bound. So this is some quantity E of G comma P. This is the minimum dimension of entanglement that's needed to achieve success probability P in this non-local game G. So here we're restricting to finite dimensional strategies for this game G. And just to give some examples, if you recall the CHSH game, this entanglement lower bound for the game for P equals to 3/4 is 0, because there's a classical strategy that wins this game. So you don't need any quantum entanglement at all. So you don't need you only need a deterministic strategy to win. To win with probability this 0.854 value, you need a two-dimensional strategy at least. And it's impossible to win the CHSH game with probability 1 with any finite dimensional strategy. So we say that the entanglement lower bound is infinite. Okay, so with this notation setup, I can describe the main technical workhorse of this of our work, which is something I'll call the compression theorem. So what it says is that there's some computable map that I'll call compress, and compress will map uniform families of games to uniform families. So if you walk up to me with the family G sub n and you apply compress to it, which really means you take this single Turing machine G hat that talks about this uniform family of games, and it'll output another Turing machine F hat that specifies another uniform family. And what's the relationship between these two families of games? Well, the output of this compress procedure is games Fn that have very low complexity. So for all n, the complexity of F sub n is going to be polylogarithmic in n. And this is true without any conditions. So compress is always going to produce these low complexity games. And if it happens that the input family that you provided has polynomial complexity, so if the complexity of G sub n is equal to some fixed polynomial in n, then we have these this relationship between Fn and Gn. So we have this completeness preserving property. So if there was if the quantum value of G sub n is equal to 1, then so is the quantum value of F sub n. And we also have this dimension lower bound. Okay, so this relates the minimum dimension strategy that you'd need to play F sub n to win with probability at least a half. And it actually gives two lower bounds here. So one lower bound is that you need at least 2 to the n dimensional strategies to win F sub n with probability a half. But you also need whatever entanglement was needed to win G sub n with probability half. Okay, so there's these two lower bounds. Right. So this compression theorem is the the most important technical slide here. So maybe I'll just give a couple seconds to people to mull over it. So let's see how we use this compression theorem to get this reduction from Turing machines to non-local games. So this is how we do this recursive compression. So fix your favorite Turing machine M. I'm going to define a uniform family of games Gn that depends on M. So for every n, this is how the game Gn works. And I'm going to specify this pseudocode. So think of this as the computer program that tells you how to play this game Gn. So the first thing the verifier is going to do is run this Turing machine M for n time steps. And if within this time M halts, then the players just automatically win. It doesn't matter what answers they produce. They just automatically win. But if M doesn't halt in this time, then the verifier is going to continue on to steps 2 and 3. It's going to compute the compression of this family Gn. So notice that there's some self-reference going on. It's going to compress itself of this family of which it belongs to, and it computes this new family F, and it's going to play the n plus first game in this new family. So, what are the properties of, I've defined this game G sub n. So what are its properties? So first, we'd like to know what is its complexity. So let's do some accounting. Well, the first step takes n steps, right? That's just by definition. The second step takes a constant, it takes constant time. And that's because we're just running compression on this uniform family. You're just running it on this constant size object that doesn't depend on the index n, right? You're running it on this G hat object, which is just some fixed Turing machine. And then you're going to play the n plus first game of this family, which is guaranteed to be very low complexity, right? It's polylog n plus 1. So if you add up all these complexities together, you get something that's clearly, something that's linear in n. So really, the complexity of G sub n is some polynomial in n. And therefore, by this compression theorem, we know that this output family Fn is going to satisfy all the conclusions of the compression theorem, right? Including this completeness preserving and the dimension lower bound conclusions. Okay, so the more interesting thing is, well, okay, so let's go back to the compression theorem for a sec. It's a good thing to look at. So any questions about what's listed here? Okay, so so now we want to look at what's the quantum value of this game G sub n. There's two cases to consider. One is case one, this Turing machine M halts in some finite time t. Okay, so the easy thing to see is that if the index n is greater than this time t, then trivially the quantum value of G sub n is going to be equal to 1, because we always just accept in step 1. But if n is less than t, then by construction, this game G sub n is always going to be the same as this compressed game Fn plus 1, right? So therefore, their quantum values are going to be equal. So now this is where we use the compression theorem, and we relate the value of Fn plus 1 back to Gn plus 1. Okay, and so let's see. Right, so by the compression theorem, we know that since the value of gt is equal to 1, therefore ft has value 1. But then propagating things downward, you get that the quantum value of gt plus t minus 1 is also 1, right? So you just rinse and repeat, and this sort of percolates down all the way to g sub 1. And you know that all the games in this family have value 1. So we know this as a fact. So that was easy. Now, what about the other case? Now suppose that this Turing machine M never halts. Well, what can we say? So we know, in this case, step 1 of this Turing, this game G sub n never accepts. So we're always just playing this compressed game Fn plus 1. So in particular, the lower bounds of the entanglement lower bounds on these two games are always going to be the same. And now let's apply the dimension lower bounds that we know for the Fs. So we know that, for example, the entanglement needed to play Fn plus 1 is at least the entanglement needed to play Gn plus 1. And if you just rinse and repeat, we get that the E of Gn is going to be at least E of Fm for all integers m. Okay? There's no relation between n and little m here. So here we apply the second part of our dimension lower bound. We know that F sub m needs entanglement 2 to the m. Okay, so you see that there's no finite lower bound on, there's no, for all integers 2 to the m, E of Gn is at least 2 to the m. Okay, so in particular, we say that it's infinite. There's no finite dimensional strategy that can win G sub n with probability 1/2. Right, so that tells us that, in particular, the quantum value of G sub 1 is at most 1/2. So this completes the the analysis of the two cases. This is how we have a reduction. So for every Turing machine M, we can just map it to the first game in this family, G sub 1. And but by what we've proved, if M halts, then the quantum value is 1. If M does not halt, then the quantum value is at most 1/2. And this proves the MIP star equals RE statement. Any questions about that? Okay, so does compress need to know the whole family G sub n? Does this recursive definition of G sub n then not cause problems? Okay, so that's a good question. What does compress need to know? So let me go back to the compression theorem. Oops. So what does compress take in as input? Again, it doesn't take in any individual G sub n. It takes in the Turing machine G hat that specifies this whole uniform family. So that's how compress knows about at least implicitly, all of the individual games G sub n. It takes in the thing that specifies this uniform specification of the family. And for the second part of your question, does this recursive definition of G sub n cause problems? You're right. This how does this game G sub n refer to itself, or refer to the compression of itself? So this is not 100% obvious how to do this, but in fact, it is possible for Turing machines to, in some sense, refer to their own source code. And this is a fact that it's possible in computability theory. So we essentially use that here. So we can have this self-reference going on. So I hope that answered your question. Okay, great. So let's see, this pretty close to out of time, but let me just say a couple words about how does one prove this compression theorem. So clearly it's it's very powerful. What goes on under the hood, and I'll just say a couple ingredients that are involved. So ingredient number one is something that is called the rigidity phenomenon of non-local games, and so to explain it, let me go back to the CHSH game that I described in the beginning. So the CHSH game, not only does it have this separation between quantum values and classical values, it also has this uniqueness property. So optimal quantum strategies are essentially unique. If you walk up to me with some quantum state psi, right, this unit vector, and some measurement operators that succeed with this optimal cosine squared pi over 8 value, then I can actually show that there's a change of basis under which the state psi and these measurement operators have the following form. So in particular, the state psi is going to look like something known as the EPR pair. So this is a state, this is a four-dimensional state and it's in tensor product with some arbitrary other state phi. And more importantly, these measurement operators, for example, the box A's measurement operators under this change of basis look like the following matrices. Okay, so they look like these two-dimensional matrices, and really it's saying that whatever crazy strategy you walked up with, it could be a million dimensional or whatever. Really, what's going on under the hood is this two-dimensional strategy inside. And they all look the same under this change of basis. And so, we can say that this CHSH game certifies two-dimensional strategies, right? So, you're playing the CHSH game with these two boxes, and if they're winning with probability that's, this cosine squared pi over 8, then inside these two boxes is at least some two-dimensional Hilbert space. Right, so one question is, did you say that the EPR state is four-dimensional? How does this fit with the 2D nature of A00? So it's because this EPR pair is split between the two boxes. It's really the tensor product of two-dimensional pieces. So HA and HB are each two-dimensional. So when you take the tensor product, you get something that's four-dimensional. But the A's only act on HA, so that's why it's 2D. Yeah. Okay, so the CHSH game has this uniqueness property, this rigidity property, and a bunch of other non-local games also have it. This really the workhorse of this compression theorem is something called the quantum low degree test. So it's a non-local game that has very sophisticated rigidity properties. So it's a family of non-local games that for all n certifies n-dimensional strategies. Okay, so all strategies that win this quantum low degree test must be at least n-dimensional. Okay, And but the significant part is that the complexity of this game is only polylog n. Okay, so it's a very efficient game that can certify a large amount, a large dimensional strategy. So that's one ingredient. And then the second ingredient is this PCP theorem that I mentioned. Okay, again, it states that proofs can be verified by examining only a constant number of random locations in the proof. So to illustrate this using a cartoon, imagine that some aliens came down to Earth and they announced that they had a 20,000 page proof of the Riemann hypothesis. Okay, and of course we would be very interested, but the limits of our brain power prevent us from fully digesting all the complexities in this extremely complicated proof, right? But this PCP theorem says it's possible to perform a PCP encoding of this extremely long proof. But now we have the property that we can verify the correctness of this proof by examining 3 locations in this proof chosen at random. And we'll with high statistical confidence, we'll know whether this proof is correct or not. Right, and this statistical confidence is over the randomness of our choice of locations to look at. Okay, and we can determine whether the Riemann hypothesis is true or not. So how is this amazing encoding used? Well, in this compressed game f sub n, what the players are supposed to do is they're supposed to generate a PCP encoding of a proof that the original game G sub n had a perfect winning strategy. And the verifier in this game can check this purported proof extremely efficiently. And this is why this game f sub n has such low complexity. And it's, again, due to this PCP theorem. Let's see, so Ilias says that what assumptions do you have on the format in which the alien proof is written? So the only assumption is that we agree, everyone agrees on, using some, axiomatic, logic system, maybe like, a ZFC or something like that, that everyone agrees on a formal way of formalizing mathematics, but it's just that their ZFC proof of the Riemann hypothesis was just way too complicated. So this PCP encoding will make it more easily checkable. Okay, so I'm over time, but this brings me to that's the end of the talk. So there's a bunch of open questions. One is whether there's a simpler, shorter proof of MIP star equals RE or its consequences. One might even hope for maybe a PCP checkable proof. And of interest probably to many of you is how can one construct an explicit 2-1 factor that doesn't have this Connes embedding property. So I mentioned earlier that we have an explicit non-local game that has differing quantum and commuting operator values. If one could write down what the commuting operator strategy looks like for that game, you would have such an explicit factor. But maybe there are easier ways of doing this. Another interesting question is constructing a non-hyperlinear group. If this non-local game that has this, that separates commuting operator from the quantum values could be cast as what's called a linear system game, or binary constraint, or what do you call it? Linear system game, then this would immediately imply the existence of a non-hyperlinear group. But we don't know if our games can be written this way. And finally, for complexity aficionados out there, there's a question of what is the complexity of approximating the commuting operator value of games. And the conjecture is that this is equivalent to co-RE. Okay, so that's it. And I just want to end with an advertisement. If you're interested in more of these things about MIP star, I've set up a wiki page on my home website called mipstar.henryun.net. It has links to different resources, such as different reading groups that people have set up around the world, and they have their notes and And hopefully it's going to be a useful and helpful resource for understanding what's going on in this work.